Hello everyone, we are learning the subject of electromagnetics, or you can say electromagnetic field theory, and we are going to continue the chapter of your the wave propagation, and especially on that the particular topic is nothing but your the waveguide. Okay, so today we will continue. The topic is nothing but your the waveguide modes. Yesterday we have seen the basic concept which were related to your the wave propagation of your the electromagnetic waves. So what is here in the waveguides, that is too important. Why we are learning this waveguide, that is also too important. So in the electromagnetic wave, whenever the waves are traveling, whenever the waves are passing or any signals is in the transmission line or the waveguides, so they need to use the different kinds of the modes. The mode is nothing but they are showing that taking a care of your the different materials, how they are passing, what are the properties of that, what is the necessity of that, how they can ensure the correct what we can say the excitations given by that modes, depending upon the whether they are traveling in the electric, whether they are traveling in the magnetic, or they are traveling in the both. That is too important. So we should decide first how we how our wave can be travel, how the excitation given to that particular wave. So that is nothing but here the waveguide modes. So in this waveguide modes, we are having various kinds of modes are available. So n number of modes are there in that. N number means more than one modes are there in the waveguides. Okay, so that we are learning today. Number one is nothing but you are the TE modes. So TE mode denotes as a transverse electric waves. Okay, transverse electromagnetic waves. So in short, T is nothing but the transverse and E is nothing but the electric. Okay, so transverse electric field or transverse electric modes or the transverse electric waves. So this is depend upon the transfer electric wave, that is also known as your the H wave. Why we are telling the H wave? The wave which is traveling, that is no doubt at all in the form of your the electric waves, but that electric waves is also known as your the H wave because they are showing the characteristics related to the magnetic field, even though they are passing on traveling in the form of a sinusoidal waveform. But if the representation comes, we know very well the electric field is represented in the E and the magnetic field is represented in the H form. If the electric flux density is representing in the D, whereas magnetic flux density is representation in the form of your the B. So keep remember this is this giving the information or the characteristics or the waveform related to the electric wave, electric field, no doubt at all. But we are finding the parameters by the reference of this electric wave, that is nothing but the H. That's why such type of wave is also known as your the H waves. Similar to that, the second mode of operation or the second mode of your the waveguide is nothing but the TEM modes, or the that is nothing but transverse magnetic waves or the transfer magnetic field waves or the transfer magnetic mode only. Okay, so this is also known as your the E waves. The name is nothing but the wave which is traveling in the form of your the magnetic, but by traveling on that magnetic waves, giving the parameters which are related to the electric wave, because these are known, this is the unknown, so we are finding this unknown. So in short, you can say this is nothing but the E waves. Okay, which are characterized by the fact of your the magnetic vectors, and we know very well magnetic field is H. If we are having the field of the H, but we are finding the unknown, that is nothing but the E waves. Okay, or you can say they are perpendicular to each other. In short, already we have studied in the uniform plane wave, already we have studied in the water transmission line, that is electric as well as the magnetic fields are perpendicular to each other. Okay, they are traveling in the space, they are traveling in the transmission line and other wave in the particular direction. So that wave are propagating, but they are perpendicular to the each other. The third is nothing but the TEM mode, that is nothing but transverse electric magnetic mode, transfers electric magnetic waves, that is nothing but the combination of your the TE plus the combination of your the TM mode is nothing but equals to your TEM. TE plus TM is nothing but TEM mode. Okay, so this is this wave gives the complete picture of your the TE as well as the TM modes. Okay, this type of mode is commonly used within the coaxial cable, you can say, are also applicable and the useful whenever there is a open wire feeders are there. This TEM wave is characterized, that is both the electric as well as the magnetic field. In short, you can say the both the vectors, they can give the information about the both the vectors, that is electric E vectors as well as the H vectors. Okay, which are already we know they are perpendicular to each other and they are traveling in a particular direction, or they are propagating in a particular direction. So in this way we can say the mode of propagation, how we can find. So see here in the TEM, which is the combination of a TE plus TM. If we observe, if I am talking about my TE mode, which is the transfer electric mode. So in this TE mode, the electric lines or the electric flux of lines are perpendicular to the axis of your the waveguide. So which are the two axes? So here two axes are nothing but one is the x coordinate, other is nothing but the y coordinate. Okay, one is the x coordinate, other is the y coordinate. If I'm taking the reference as my T is the x coordinate, so definitely my TM will be the y coordinate. That's why the remaining part is nothing but the z coordinate, which is not going to propagate. Only the propagation is going the x coordinate as well as the y coordinate. That's why we are taking here the z is nothing but the zero form, that is the Ez and the Hz, that is electric fields in the z direction and the magnetic field in the z direction will be treated as a zero, just because there is no propagation is going on that particular coordinate system. Only which things are working, that is the x coordinate as well as the y coordinate. One time x coordinate is acting in the electric field, treating as a electric field, whereas other y coordinate or vice versa, it doesn't matter, or the y coordinate in the magnetic field, they are giving the propagation information in the field of electric as well as the magnetic, but the x as well as the y coordinate, and rest of the one remaining, that is the coordinate, that is nothing but the z, will be treated as a zero here. How we can write the equation of your the TE, TM and other modes, that is too important. So we are this figure already we have studied in the unit number 1 in the vectors. Okay, so these parameters, anything you can shuffle, here maybe the xyz, here maybe the xyz, here maybe the any xyz. If you're taking here the y, x, z, or you may rotate anything, and if there is a spherical box is there, and if you are interested to find out how my wave is propagating, that time you must take care what is my the horizontal length, or what is my particular, that is a width and the length, that is too important here. So in this case also they are representing how we can write the equation, both the equation. Okay, that is nothing but your the that is x equation as well as the y equation. But if you're talking about the M, that is a transverse magnetic mode, so we know very well we are writing that equation of your the boundary condition is nothing but in the form of your the Ez, because the x and the y they are acting, but the Ez is the zero. If I am saying if my Ez is a zero, so how I am saying Ez is zero? Because the representation is in the x and the y. If I am talking about, if I am writing the expression for the y, see here my vertical form y, which is starting from 0 point here to the b, 0 point here to the b. And if I am writing the equation and the point which is at this horizontal point, so that is nothing but 0 and the a. So here that's why x coordinates are nothing but 0 comma a, whereas y coordinates are the 0 comma b, and the entire x and the y are present, but the z term is nothing but the 0. That's why if we are going to write the entire term of your the boundary likewise in the form of your the x and the y, okay, so sine and the cosine, so you can write easily, and the constant term also you can write. And these m and the n are nothing but the representation of your the n number of your the modes, n number of your modes depending upon the frequencies are availability. So these are the commons, a1 and a2 are you may treat as the vectors, already we done in the unit number 1. Cos and the sine form is totally depend upon the coordinates x and the y. Likewise you can write the expression. Okay, now the next is nothing but your the how we can find the parameters, rest of the parameter in the TM modes. What is the next parameter ultimate? If I am having my ex and I'm having my ey, so what is this representation? This representation is nothing but the ex and the ey. So this is the what we can say the peak value of your the electric field. Okay, peak value of your the electric field Ez. Okay, peak value of electric field in the direction of your z by the combination of your the coordinates of your the x and the y, okay, with exponential form. So here m as well as the n will be the representation of a different number of modes are there. A and the B are nothing but on the x and the y axis, the coordinating points are there, and this is the peak electric field magnitude of the peak electric field is there, and this one is the exponential form. Later on you can find in which particular mode is there, okay, in which particular mode, how you can define the height of that. So that is also possible. This is the constant value, this is the propagation constant, and you can find this A and the B depending upon the value of your the x and the what we can say at the x coordinate as well as at the y coordinate. So in this way the m and n, which is the representation of your the mode of propagation, and also indicating how the number of variation of the field is occurring in the x as well as the y direction. So while you're going to study again, we need to think about the parameters. Always we know we have studied in the uniform plane wave also, how we can find if my wave is propagating uniformly, how my wave is propagating in the transmission line, whenever my wave is propagating in the optical wave or the sound wave or the sky waves, whatever you are taking as a medium. So the parameters will be there, which we need to calculate. Just like one of the example is a propagation constant, the example is attenuation constant, the example is a what you can say phase constants, the example is of your the impedances, the cutoff frequencies. So these are the things that we need to calculate, and totally depend upon the things we can calculate easily. That is nothing but if I am talking about the transmission line, the things will be the different. I am talking about the optical waveguides, that will be the difference. So similarly here the change you can observe easily, the propagation constant gamma is equals to alpha plus j of beta. Instead of that here we are writing this propagation constant for the TM mode. So we can write here, how we can write that is in the form of your the x as well as the form of your the y by looking that coordinate. So my propagation constant, which is denoted by gamma, is equals to root of the x term and the y term square, along with your the common constant term is squaring. Means by looking that you can say the resultant one. If horizontal is the x or the a point, vertical is the y and the b point, the resultant ultimate in the slanting form is nothing but my k constant, which is the combination of your the x as well as the y. So the total minus of that the resultant one, you will get the propagation constant. How you can represent that propagation constant in other way, that is mentioned here. One which is the related to the x is nothing but m pi by a, and one which is related to your the y coordinate is nothing but n pi by b. So both are squaring, and what is my k will be equals to omega square mu epsilon. What is my mu and epsilon? That is nothing but if you're talking permittivity and the permeability for the reference point, that is mu 0 and the epsilon 0. Okay, so you can write that constant value, you can find easily by substituting the value of your the what we can say the mu 0 and the epsilon 0, you can find easily. Okay, so here also the cutoff frequency can be occur whenever you are writing the expression for your the propagation constant, which is in the form of alpha plus j of beta. If you are treating as in that term is a 0, but if this term is 0, so definitely by removing this root term, you can find a squaring on both the side, you can do it, and you can calculate the omega c square is nothing but mu and epsilon and other parameter. Likewise the cutoff frequency will be equals to 1 by 2 pi, that is nothing but we are substituting the value of your the omega. Okay, that is omega is nothing but 1 by root of so. So in this way you can find the expression, you can calculate the unknown parameter, you can substitute the known parameter values. Okay, so here you should keep remember that whenever these things are happening, omega square mu epsilon, it will be lesser than this. So at that moment the alpha the propagation constant will be equals to alpha attenuation constant, because the phase constant will be treated as a 0. So in this way no attenuation at present if there is no phase angle. Okay, if whenever we are is a greater value, that time instead of real term here will be the imaginary term, and attenuation constant will be 0. So be remembered, if angular velocity is greater, definitely the imaginary part will be affected and the attenuation constant will be 0, or vice versa cases. So come to the point again, the cutoff frequency, how that can be represented in the form of the curve. So that is the attenuation. If 0, that is nothing but we are not concentrating the attenuation. So here will be the 0 point, and later on the cutoff frequency is affecting in the form of the what you can say, the modes, that is Mn, and then you can find easily the propagation of a mode in the Mn. So how we can find finally the cutoff frequency in the Mn? That is nothing but u dash, the change of the energy. You can find easily u dash divided by 2 root of m square by a and n square by b of whole square, and you can substitute. The second is nothing but how you can calculate the beta. Beta is nothing but root of this omega square mu epsilon minus of so and so. These are the subtraction. And finally, if you don't have that value of m, n, a, b, so you can alternate formula related or alternate expression related to the phase constant is nothing but root of 1 minus fc by f whole square. So in this way we can find the velocity, phase velocity. Okay, many times the notation in the textbooks are nothing but you hear the up. Okay, so that is nothing but the angular velocity, angular frequency divided by the phase constant lambda, that is a wavelength. You can find 2 pi by beta. This is nothing but the propagation of phase velocity, or the velocity of propagation up. The notation may be changed. In many of the textbook they are referring the vp, many textbook they are referring only v. Okay, likewise. So we concentrate, we focus on how you can take the notation. So second is the intrinsic impedance, how you can calculate for the particular mode, whether it's a te, whether it's a tm, whether it's a tem. Okay, so in short here, you should note down while you are going to simplify. That is nothing but you are the eta, whether it's a tm, whether it's a te, whether it's a tem, how you are going to write the expression. So we remember the cutoff frequency, we remember the propagation constant, we remember the alpha, we remember the beta, we remember the eta, we remember the impedances and all, we remember the 5. These are the basic lambda. So these are the basic values, parameters. While you are going to simplify, you need to keep focus on that, how you can find out the thing. Okay, so in short you can say, and you can find the rest of the thing. See here, if E is in the x direction, H is in the y direction, definitely the other thing other will be in the z direction, that is in the resultant form. Likewise, you can find easily the parameters. So see here, this is nothing but the summary of your the TM mode. Why I am writing here the summary, that is a wave in the dielectric medium, how the wave will be inside the waveguide. See here the difference between these two. In this way, you can find if my wave is in the dielectric medium, what how I can calculate my propagation constant. If my wave is inside my waveguide, how I can calculate my propagation constant. That is important here. Similar to that, that's why they written here the beta dash and the beta, just because of the difference between the dielectric medium and the waveguide medium. So here also the eta, that is a characteristics impedance. Here the eta for the TM, they mention clearly, maybe the TE, maybe the TEM. Likewise, you can find the parameter. Here the velocity of propagation also you can find easily with the help of the angular velocity as well as the phase constant. That is nothing but the by concentrating the wavelength and all. See here the how I am taking the v dash, or you can say the vp dash, and the last is nothing but here the wavelength. You can say, we can say the wavelength. How we can find this wavelength and how this wavelength is different in the dielectric as well as the wave. Getting? So now the next method is nothing but you are the TEM. Sorry, TE mode. Okay, first is the TM, second we have studied the TE mode. So in that, how I am writing the expression for my H. Previously I have written my expression in the EZ. Now I am writing the expression in the HZ. Okay, in this way the my vector will be changed, that is the B form, the B1, B2, B3 likewise. Okay, the cos and the sine term will be as it is, K term is the constant will be as it is. These are the X coordinates and these are the Y, and exponential will be as it is. How I can write the expression for the boundary condition, that is Ex is equals to 0. Okay, X term is 0. How I am writing the X term is 0 and Y term is 0, just because on the X axis at the initial both are the zeros, and then later on 0 to A, 0 to B. So at the initial stage there is a 0 to A, 0 to B. Likewise the X is 0, Y is also 0, but the next time the X will be up to the A that moment, and the Y will be reached up to the B. Okay, So in this way, the plane will be the 0, the cos and the sine can be calculated, the constant kx and the ky, that is nothing but the constant value at the x coordinate, constant value at the y coordinate can be determined with the help of m and n, the value mode, different mode of operation you can find easily. In this way, finally you can get the what you can say, the boundary conditions or the magnetic field in the z direction. You can find easily with the help of the vectors. So here again, in the TE mode, how I can represent my HZ, how I can represent my H square, how so we can calculate the known parameter. That is nothing but here also, instead of E0 in the previous slide, that was E0. So here is the H0 if I am writing for the TE mode. If for TM mode, then the E0 cos of so m pi x divided by n pi by b of y. And this one is nothing but the exponential form. Likewise, you can find this hollow type. Okay. See here the cutoff frequency for the Tm, that is attenuation constant. From this particular, you can find the Tc. I mean, that is nothing but cutoff frequency. See here the difference, the wave propagation. Okay, velocity of wave propagation divided by 2 root of m by a and n by b. Likewise, you can find the cutoff frequency of your that explosion. So here you can observe easily here the lower frequency ranges. That's why we are not taking any kind of the frequency. That's why the attenuation is 0 here. So dominant mode, which is the dominant mode. So here the number is mentioned Mn. That is nothing but you are the in which mode. But there is a mode of operation decide, and this is totally depend upon the wavelength and the frequency ranges. The one of the slide is there on this basis. I will show you soon. See here again the summary of your the TE mode. How I can find the propagation constant, how I can find the intrinsic impedance, how I can find the velocity of propagation, how I can find the wavelength. Okay, all these cases are in the not only in the dielectric medium but also in the waveguides. See here, this is the characteristics curve between the impedance, intrinsic impedances. If I am talking about the wave impedances, which is varying with the frequency and the modes. So here they clearly mentioned the TE here, bottom is the TM, and the combination is nothing but TEM. So in this way, you can find how gradually the frequency is changing. Okay, how gradually the frequency is changing. That you can find, you can identify easily. Okay. How we can simplify the numericals, the exercises, what will be the cases so that we can identify one of the example like is mentioned here. One of the example we can mention here, consider the length and the air field of copper. X band is there and the wave guided with a dimension is given, that is A or B dimension is given, and the operating at a particular frequency. You can add if the A and the B value is given, operating frequency is given, you can find the other parameter. Okay, how we can find, that is the cutoff frequency, all the propagation modes. So this is the one of the example of finding the cutoff frequency. If you are having the values, that is nothing but the velocity of propagation divided by 2 root of m square by a and n by b of whole square. You can substitute because of air field is there. The 5 by 2 centimeter waveguide is having, this is the expression of Ez, that is a 20 sine 40 pi x sine 50 pi y e raised to the power minus j beta of x volt per meter. So here the 20 will be the either the E0 or the H0. Okay, E0 or the H0 at a particular frequency, nothing but the 15 gigahertz. Okay, so here what we should think while we are learning, doing this exercise, we should concentrate which mode we are using, in which mode the wave is propagating, how I can find the propagation constant, phase constant, attenuation constant, how I can determine the EX, EY and the EZ coordinates. That is too important here in this case that we have tried to explain you. Similarly, if you are talking about the antenna designing also, we should take care the velocity of the ground. Here the G is representation how the wave are traveling. See here the reflection and the refraction form. Okay, how the angle is differ, how they can start from this one, that is mentioned here. Okay, these are the in the what we can say imaginary part, that is the j omega mu by h square pi by a. So in this way, you can find easily the group velocity, that is nothing but the UG, and the velocity at a particular wave, that is whenever the wave is traveling or the energy is inducing in that. How we can find that group velocity is mentioned here, 1 by tau beta divided by 1 by tau omega. Okay, angular velocity and the phase velocity. Likewise, you can find easily. See here the differences, that is the UP is nothing but velocity of propagation, UG is nothing but the group velocity, and this is the multiplication or the product is nothing but the velocity of propagation. See here the high frequency ranges, medium frequency ranges, low frequency ranges. If high frequency is there, how the refraction and reflection takes place, incidence is happening, how the incidence is happening, how refraction and reflection takes place is going on. See here. See the difference between the high frequency, medium and the low frequency ranges. How the frequency can be increased with the group velocities increases. See here. See here how we can find the power in the transmission line by with the help of the pointing vectors, that is a P average is equals to 1 by 2 RA, that is a real term in the electric as well as the magnetic field is mentioned here. And already we have simplified few numerical in the uniform plane wave, that is average power or the with the help of the pointing vectors. Okay, so P average is equals to 1 by 2 RA in bracket I electric field as well as the magnetic field. In this way, you can write that expression. You can find in the magnitude form. If you don't want the real imaginary, then you can convert it to the magnitude and you can find easily, and you can measure that average power in the watt per meter square. Even you can find the intrinsic impedances. If you are having that time, you should mention clearly, that is whether it's a TE, whether it's a TM, whether it's a TE, and likewise that situation will be changed for each and every mode. The situation will be changed. The intrinsic impedance for the T will be different, the intrinsic impedance for the TM will be different, the combination of both. So here we were interested in the magnitudes of the electric field in the X as well as the electric field in the Y direction. And this way you can calculate the average power and all. Here we are trying to explain about the attenuation in the lossy waveguides. When the dielectric inside the guide is lossy and the walls are not perfect conductors, so power loss will be there while that waves are traveling along the guides. So this OPF